Good afternoon, everyone. Thank you all for joining Alchemy's monthly webinar series today. So my name is Adam Clayton. I'm an associate professor in digital chemistry at the University of Leeds. I'll be hosting the webinar this afternoon. Before we make a start with the speakers, just wanted to highlight a few of the upcoming events hosted by the Alchemy Hub. So we've got the AI-infused Sustainable Manufacturing Symposium in London on the 11th of November, the Agentic AI Symposium in Liverpool on the 26th of November, and a winter school in robotics and AI for chemical materials, also in Liverpool on the 8th to the 12th of December. So if any of those events sound interesting to you, please do support the Hub and get signed up to those. So the Alchemy Hub, for those of you who don't know, is a UK hub funded by EPSRC with a vision to pioneer and normalise the use of AI for chemical research. These are the monthly webinars, and today we have two speakers lined up, each of which I'm sure will share insightful talks, followed by a Q&A session after each presentation. So our first speaker today is Yushu Han, who's a PhD candidate at the University of Liverpool, focusing on materials discovery through automation workflows. So if you want to share your slides, Yushu.
Yeah, thank you. Hi everyone. My name is Yushu Han. I'm a PhD candidate in Cooper Group at the University of Liverpool. So today I will talk about how we accelerated porosity screening. So if today's talk interests you, so please feel free to reach out via the email. First, I'd like to start with the materials I have been working with. That is porous materials, such as the activity carbon, zeolite, porous polymer, and metal organic framework. And they are offered a high surface area, defined per architectures, and turnable chemistries. They are widely used in some applications from the gas separation, carbon capture, and catalysis. And each class has their own strengths, and for the different application, they demand very specific properties. So this diversity makes the porous materials an ideal test bed for the AI-driven discovery. Their vast chemical space and the turnable structure provide the perfect playground where AI can accelerate the candidate generation and the property prediction. So, but the question is that how can we systematically explore this enormous design space? So to address this question, we turned to a closing loop workflow for the material discovery. So this circle integrates the four steps stage, like the design, make, test, and analyze. And in the design stage, the computational models generate the candidate structure and predict their properties. And those prediction then feed into the make stage, where the automated platforms enable the large-scale synthesis and word reaction optimization. And the next comes to the test stage. And depending on the material class and word application, different characterization method are demanded to evaluate their structure or the performance. And finally, in the analyze stage, the results are stored or compared and feedback to refine the models, closing the loop. So this workflow accelerates the discovery and ensuring that the AI doesn't just propose the new materials, but also learns and improves from the experimental validation with the every circle. So in this talk, I will highlight our contribution to the test stage, where the rapid screening plays a critical role. So first, for the test, we are talking about the high throughput screening, because for the different application, we require the different measurement method. But the aim is always the same, is that to achieve the high throughput screening and efficiently identified the promising candidate. So for example, like PXRD, powder X-ray diffraction, we can use it for the crystallization screening. So with an automated workflow, we can analyze the 96 well plate, and each sample takes only about 10 minutes and require just 2 milligrams of the materials. So this allows us to rapidly confirm whether a material has formed the expected designed crystalline structure. And however, when it comes to the porous materials discovery, a porosity check is essential, and this is where the real bottleneck lies. I think every chemist working on the porous materials has used a gas adsorption analyzer at some point, and it's the gold standard technique, but it always comes with some certain limitation. The first one is the extremely low throughput. So normally, about the 6 samples will take about 24 hours. And also it only provide like a 1 or 3 or 6 analysis port. And it requires the skill, the preparation, and the extremely low temperature and the pressure for the analysis. So even our group is fortunate to have the 5 analyzers. The throughput is still far lower than what you could achieve with just 1 well plate. So think about if you have the 100 or thousands samples generated from the high throughput synthesis robotic platform. You definitely want to know its porosity in a quick way. So this mismatch, like between the synthesis and the measurement, the throughput is exactly the challenge we set out to solve. So for this question, we developed the 2 new methods for the rapid porosity screening. So both platform can cut the measurement time from the 9 days down to the 36 hours, as little as the 12 hours for about 50 to 96 samples. So for the first method is colorimetric array. So we ask a simple question. Like since many porous materials are designed to absorb the dye molecules, so could we flip that around and use the dye adsorption as a proxy for the porosity screening? So we begin by selecting the 6 dyes with distinct optical absorption, chosen to cover a broad range of the molecular size and the polarities. And we screen the dyes for the solubility and the selectivity. So this process results in a 6 dye. And then to validate the concept, we set up a control black box system for the computer vision analysis. We then tested the dye array against the 4 commercial available materials, 2 porous and 2 non-porous. And the results shows that a clear distinction like the porous sample caused significant fading in multiple dyes, and will the non-porous materials retain their color. And next, we evaluate the assay on a more challenging set of the molecular solid, the materials with much more lower porosity and also different chemical groups. So this allows us to benchmark the response between the different like a porosity from different materials. And at the same time, we can assess the chemical stability of the dye array. And the result shows there are 2 porous materials respond to the dye array, and it shows the 2 or 4 color fading among the 6 dyes. So based on the average score, like the observed this molecular solid, we establish a general threshold for the assay. That is, a materials was like classified as the porous if it shows at least 2 heats. So conversely, if the sample fails to meet this threshold, it is categorized as the non-porous. And then we extended our screening library beyond the molecular solid and to consider the other 3 representative class of materials, like porous organic cage, conjected macroporous polymer, and the metal organic frameworks. So by using a semi-automated workflow, our colorimetry method is roughly 30 times faster than the conventional porosity analysis. And if with a greater parallelization and automation, the speed could be increased even further. So together, across a set of the 50 published porous materials, this method achieved a good classification accuracy. And another strength of this method is flexibility. The threshold for the classifying a sample as a porous can be adjusted, for example, by changing the number of the heat. And in addition, the design of the dye array itself is customizable. We can use the 6 dye array for the full coverage, or reduce it to the 3 dye array for the faster or more targeted screening. So it means this platform can be tailored to the different material system and the research need, and make it a useful tool for the porous material discovery. And the limitation of this method is about the water. So this method is conducted in the aqueous condition. So this can be the limitation for the lab scale materials that are not designed to be water stable. So if you are thinking you want to test the water unstable materials for their porosity screening, so we should use the second method. So to broaden the scope beyond the dyes, we developed a second method, a multi-well infrared colorimetry platform. So we ask a similar question as the before, since many porous materials are designed to absorb the CO2. So could we use that the temperature change, or say the thermal response during the CO2 absorption as a proxy for the porosity? So in practice, we dispense the materials onto a 96 well plate and place it in a sealed chamber and expose it to the CO2. When porous materials absorb the CO2 and they release the heat, we can capture this thermal signal using the infrared camera. And each CO2 dosing circle produces a thermal time series from which we can extract the features such as the peak temperature, temperature change, and the integrated peak area and other absorption kinetics information. And here is a short demo of the platform in action. So during the first CO2 dosing, you can clearly see the valve containing the porous materials light up as the heat is released during the absorption. And once dosing stops, the heat dissipates into the plate until the equilibrium is reached. You can see that on the upper left hand, the pressure is not increasing anymore. And the entire analysis only takes about the 40 minutes per plate. So right now we are waiting for the second dosing, next time dosing. As it begins, the same well light up again, and confirming that it is not only the absorption response, but also its reproducibility from the physical absorption. So to summarize, let's compare these 3 methods. So on the left hand, the gas absorption analyzer remains the gold standard. It provides the most detailed porosity data, which cannot be replaced by the new screening method. So, but it has a certain limitation in terms of the throughput and the automation. So the other 2 new methods we developed address the different resources and the material classes. Most importantly, they cut the screening time from the weeks to days and reduce the sample requirement from the hundreds to just the tens, and minimize the reliance on the complex absorption measurement, and the manual intervention. So together, it helping to close the loop, close the gap between the synthesis and the characterization in the porosity screening. and or say for the porous material discovery. So finally, thank you to Andy Cooper Group and all my colleagues. We are come from the really diverse background, but we are working on the same goal about the accelerating the material discovery. So thank you, my colleague. Thank you all.